Welcome to this explainer on the PTSG Core project. You know, we hear a lot about AI writing software code these days, right? But today we're looking at a massive breakthrough from May 2026 by Mr. Tsuneo Onaka that proves we are entering a wildly different era of engineering. We're talking about AI fundamentally taking over physical hardware design.
I want you to just imagine this scenario for a second. You hand an AI a single sentence, plus a 5-chapter spec document, and you tell it, build me a working processor in Verilog, which, by the way, is the complex language used to design actual microchips. No coding whatsoever, zero intervention. I mean, it sounds completely like science fiction, doesn't it? But amazingly, this actually happened. And this really brings us to what design automation by AI truly means today. Look, for decades, engineers have just painstakingly hand-coded hardware. Testing, revising, basically endless manual labor. We are now witnessing a dramatic evolution in AI design. The AI isn't just some glorified autocomplete anymore. It is autonomously executing a flawless hardware implementation, entirely driven by a human's core design philosophy.
To really grasp the secret of the PTSG Core's extreme efficiency, let's contrast it with what we usually think of as a processor. Your typical bulky, hot CPU in your laptop is built for general computation, meaning it needs thousands and thousands of complex logic elements. But PTSG? It stands for Programmable Timing Sequence Generator. It is ultra-specialized for one exact thing: exact timing sequence control.
And because it's so purposefully focused, here is the secret to its minimal resources. It relies on just 2 microscopic memory blocks. 2! Think of it like a tiny, highly efficient brain dedicated strictly to keeping time. That minimal footprint is exactly what makes it incredibly easy to slip into tightly constrained environments where a massive CPU just literally wouldn't fit.
The backstory here is just fascinating. For months, Mr. Onaka was basically writing letters to a ghost, an unknown reader he hadn't even met yet. He poured his deep thoughts and design philosophy into these intricate documents, waiting for an AI advanced enough to actually understand them. He was laying down this perfect foundation, totally trusting that a future AI would eventually trace and execute his exact thoughts.
Well, that reader finally arrived. When that AI agent, Claude Code, was booted up on July 6, 2026, it kicked off an absolute whirlwind. In just 48 hours, it autonomously executed a 7-phase campaign. Day 1 was this massive audit of the existing specs, followed by live late-night rulings from Mr. Onaka himself. And by day 2, the AI was setting up complex error traps and delivering first-pass silicon verification.
Right out of the gate, the AI acted like the world's most ruthless auditor. It was digging up old legacy bugs that human developers had missed for weeks. It spotted a logic gap where a branch command wasn't waiting for a clock tick. And get this, it even found a contradictory loop command hiding in plain sight in the public specs. Turns out, having a machine read a document completely literally is a fantastic way to spot human errors. Now, when the AI hit some deep-seated transition problems, Mr. Onaka stepped in as a guide during a live 11 p.m. session. The AI was really struggling with a queued command, basically a do-nothing command waiting in line. Onaka praised the overall structure, but corrected the terrifying logic errors. He essentially told it, fix the terror, keep the scaffold. They collaborated right there to patch a dangerous bug while building a flawless template for the future.
The AI was definitely learning fast, but it still made some pretty fascinating missteps. Mid-campaign, it actually tried to put the emergency reset function into the exact same waiting line as normal commands. Onaka had to jump in and say, no, reset is a panic button. It needs its own VIP lane. It has to be a scheduled panic that overrides absolutely everything else, and the AI just instantly adapted and rebuilt it.
As the campaign rolled on, the AI gave the core specifications some real teeth. It created strict traps that actually caused old legacy tests to fail. Why? Well, because those old tests were suddenly illegal under the newly enforced rules. It's brilliant proof that a strict, rule-following AI will ruthlessly police its own past to ensure absolute perfection. This rigorous testing even exposed flaws in the safety nets themselves. When testing the hardware's rescue path, the AI discovered that sure, it successfully restored the program counter, but it never actually returned the machine to a run state. A rescued core would just stand there frozen forever. It perfectly proves the old engineering adage, a rescue path simply doesn't exist until it is actually tested. Now, Mr. Onaka didn't just brute force this whole thing with one massive AI. He used a really smart economic strategy called model tiering.
He deployed the highly advanced and expensive Fable 5 model for the heavy lifting, the initial audit, planning, and final inspection. But for the repetitive, long-haul execution like code revisions and testing, he handed the reins over to the lighter, much more affordable Sonnet 5 model. Here is exactly why this matters for the future of engineering. If your documents act as perfect, flawless rails, you only need to pay for expensive, high-end AI at the very beginning and the very end. The affordable AI can confidently run that long middle section. If you write your philosophy down flawlessly just once, every future hardware campaign runs incredibly cheaply. Even after the campaign officially closed, there was one more mind-bending post-campaign discovery. At the machine's absolute smallest timescale, the AI hit a paradoxical logic loop. See, the original design assumed the machine would prepare to count and then actually count on the next tick. But at max speed, it was trying to prepare and count at the exact same millisecond.
So, how did the AI fix this paradoxical cliff? It looked all the way back at a table Mr. Onaka had written weeks earlier for his unseen reader. By tracing the strict rules of that 33-cell table, the AI perfectly resolved this incredibly complex boundary condition using just 3 lines of code. The human's initial philosophy carried its own weight exactly as intended.
I want you to just look at the sheer payload of this experiment. It started with one single specification sentence. That one prompt resulted in 19 highly specific revisions, 33 flawless tests, and 0, let me repeat that, literally 0 errors when compiled on a physical microchip org. What we are witnessing here is a closed, automated loop. A human specification seamlessly becomes reasoning, that reasoning becomes implementation, and that implementation yields hard, physical silicon evidence. These stages aren't separated by months of tedious manual labor anymore. They have become tightly integrated, machine-checkable contracts. And the ultimate victory here? This didn't just work in some digital simulation. The AI-generated code ran flawlessly on a physical Cyclone V microchip at 50 MHz on the very first try. The hardware reported 0 errors. That absolute silence is the loudest thing verification can possibly say, and it is a monumental achievement for automated design.
Mr. Onaka's vision came to life entirely autonomously, perfectly translating human intent right into physical hardware. So I'll leave you with this. If perfect documents act as the rails, how fast will the next generation of AI ride them? What actually happens when AI takes over all of engineering? I'll let you think about that. Thanks for joining me for this explainer, and definitely keep questioning what's possible.